Hey Ramblers, this video covers Chapter 1.8b, or the second half of Chapter 1.8 in our textbook. And we're going to look at what happens to limits as both the x value approaches infinity and what happens as the limit itself approaches infinity. So we want to talk about that. We're going to talk about the continuity and the definition of continuity. And then we're going to talk a little bit about how to find or evaluate limits when at first it might appear that the limit doesn't exist. So please take careful notes on this, pause often, and thanks for watching. Okay, if you recall from the last video, we remember that a limit is just a y value where we expect to find a function as x approaches a given number or a given value. But sometimes the number that it's approaching is infinitely large. Or sometimes the x value that we want to be thinking about is also infinitely large. So let's take a look at a couple of examples. The first is that what is the limit as x approaches, let's say, a number like 2 for the function 1 over x minus 2? Well, you'll recall from our parent functions that's just the function 1 over x shifted 2 units to the right. So that's going to look something like this. Now from the picture it's pretty clear that as we approach 2 on the x-axis, where we expect to find the function is in two very different places. As you can see, as we're coming toward 2 from the right side, the function is growing to infinity. And as we come toward 2 from the left side, the function is declining or decreasing to infinity. So we would say that for this limit, the limit does not exist. And it's not because it's going to 2 infinities, but because a limit has to be a number. It can't just be a concept like infinity. Now, it is worth noting that we will talk about the limit as x approaches 2 from the negative side, or from the left side, that also did not exist, but sometimes you'll see it referred to as it went to negative infinity. And on the same vein, as x approaches 2 from the positive side of 1 over x minus 2, where it's coming from the right side, we'd also say that does not exist. Or you might say it goes to positive infinity. Because while it's not technically a limit, it is valuable for us to recognize that the function is growing toward a positive or negative infinity and to have the language for that. Okay, so that's an example of where the limit itself is going toward infinity. Let's take another look at an example where it's the x number that's going toward infinity. All right, let's take a look at this more familiar function, x cubed. And here we have x cubed, we know, just increases all the way from negative infinity through the origin right up to positive infinity. So we would say that the limit as x approaches infinity of x cubed is also, we could say, does not exist. Or we may want the language to know that this approaches positive infinity. By the same reasoning, as x approached negative infinity of x cubed, so in other words, now we're looking as x is going out toward negative infinity, then this function does not have a limit, or you might say that it approaches negative infinity. Again, not technically a limit, but it's nice to have the language. Okay, those are the two places where infinity comes into our discussion of limits. So all of this brings us to a definition of continuity. Now we've talked about continuity is drawing a function without lifting your pencil. And that's pretty accurate, I guess, but we want something a little more robust that we can use to analyze different situations. And it's this, that continuity is when the limit as x approaches some value a of a function from the negative side equals the limit as x approaches a from the positive side of the function equals the value at a. So now these two together, if they're equal, they mean that there is a limit at a. Sorry, that should just be an x. And so really this definition boils down to this, and this should definitely be in your notes, that a function is continuous if the limit as x approaches a equals the value of the function at a. Let's take a look at this example. Here I'm going to put the point A, and along comes a function, and it has a hole there at a. Now clearly you can see that the limit exists. Let's call this point M, that the limit as x approaches a of this function f of x equals m. However, f of a is a hole, so it does not equal m. So this would not be continuous. Now, it's also true that you can't draw this without lifting your pencil at a. But again, we want something more robust. Let's take a look at another common place where we run into discontinuities. Okay, another place where we run into discontinuities are anytime we have an asymptote. So let's take a look at 1 over x squared. Now this function is actually sometimes referred to as the volcano function, just because it seems to look like a volcano right there along the y-axis. So whether you're coming from the left or coming from the right, the limit does not exist, and there is no value at x equals 0. It's x equals 0. So this would not be continuous, and there's no way we can fix this. Unlike the hole, where we could maybe just define a y value at that where the hole is, this one's not continuous. So let's look then at our formal definition of continuity. Okay, this is what I would make sure is in your notes. Just this part here, that if a function is continuous at x equals c, if f is defined at x equals c, and if the limit approaches, I should erase so you can see this, that the limit of f of x as x approaches c equals f of c. Okay, Ramblers, let's take a look at some implications of continuity, and then we're going to finish things off by looking at some tricks for evaluating limits. Okay, as a result of continuity, we have 4 important implications, actually 5, you'll see in a minute. Let's let f and g be continuous functions over a certain interval. And let's just make b some constant number. It can be anything, positive or negative. Then, a couple things. Number 1, that number times f of x, that number b times f of x, is a continuous function. If you add 2 continuous functions together, the result is a continuous function. If you multiply 2 continuous functions together, the product is continuous. And finally, so long as g of x does not equal 0, the quotient of 2 continuous functions is continuous. Okay, what happens when we make a composite function? If f and g are once again continuous functions, then the composite function, f of g of x, is also a continuous function on that interval. So, as long as the 2 functions are continuous, we can multiply them, add them, subtract them, divide them, and composite them, and you'll have a continuous function. Alright, one last slide on just showing you a couple tricks for finding limits when it looks like they don't exist. The first thing you should try when evaluating a limit is always substitution. And substitution is going to give you the answer about 95% of the time, or it should, because most things aren't tricky. So let's take this first limit, for example. What is this limit? Where do we expect to find this function as x is approaching 2? Well, let's plug in 2. So 2 squared minus 3 times 2 plus 2 is going to equal 4 minus 6 plus 2. That's equal to 0. Now it gets a little more interesting if we were to take the limit as x approaches 2 of the same function, but let's say we put a denominator on that. Let's say we said x minus, I'm sorry, not x, but t minus 2 down in the denominator. Now, when you evaluate it and plug 2 in, you're going to get 2 squared minus 3 times 2 plus 2 over 2 minus 2. As we saw, that's going to give you a 0 in the numerator over 0 in the denominator.
His daddy can't talk.
Look who knows so much, huh? Well, it just so happens that your friend here is only mostly dead. There's a big difference between mostly dead and all dead. Please open his mouth. Now, mostly dead is slightly alive. Now, all dead, well, with all dead, there's usually only one thing that you can do.
What's that?
Go through his clothes and look for loose change.
Now, this is actually a good sign, because when you get 0 over 0, it means do something. It means that you have a hole. So the limit does exist, likely, but you have to figure out what it is. And that something, in this case, is going to be factoring. So factoring is one of the things that you should try to do when you can't find a limit. And if you do that with this problem, you'll see that you get the limit as x, I'm sorry, I keep writing x. The limit as, oops, let's just leave it as x. The limit as t, the whole thing's shaking now. The limit as t, oh, that's much better. T approaches 2, and we can factor the top as t minus 2 times t minus 1 over t minus 2. The t minus 2's will cancel, and we're left with the limit as t approaches 2 of t minus 1, which is just 2 minus 1, or 1. So that doesn't mean we don't have a hole. We do. The value of this function is not defined at t equals 2, but the limit equals 1, and that's worth knowing. Okay, let's take a look at another trick we can play in order to evaluate some limits. Alright, let's try substitution again on this. When I plug in 0, I get 4 plus 0 squared. I'm sorry, I should be more proper. And we write limit every time. The limit as x approaches 0 of 4 squared minus 16 over 0 equals 0 over 0. And once again, that's a good thing. That means you can do something rather than a number over 0, which means you can't do it. But 0 over 0 means we can do something. So what should we do? Well, in this case, we should expand the numerator. So we'll get the limit as x approaches 0 of 16 plus 8x plus x squared minus 16 over x, which of course equals the limit as x approaches 0. And the 16's will cancel out. And so we're just left with the limit of x squared plus 8x over x. Now in the numerator, I can factor out that x, and so I have x times x plus 8 over x. Those two x's will cancel, and now I'm left with the limit as x approaches 0 of x plus 8, which when I try substitution now, I get 0. I'm sorry, I get 8. Sorry about that. So once again, it doesn't mean that we have a value for the function there. We just have figured out the limit. So we know where we would expect to find the function at x equals 0, even though there's a hole there. Okay, let's take a look at one more trick I want to show you, which comes from trigonometry. Ramblers, you may remember this limit from the video on the first half of this chapter. But this is really just sine x over x looks something like this. We've got a hole at 0, 1, and then it keeps oscillating along the x-axis. And so this function is one you should kind of keep in mind because it helps us out of some tough spots with some trig limits. So for instance, we might get something that says like this: limit as x approaches 0 of sine x over 2x squared minus x. Now, if you plug in 0, you're going to get the sine of 0 over 2 times 0 squared minus 0. You're going to get 0 over 0. But once again, that's our sign that there's a hole here and we can fix it. So let's try factoring the denominator. So we get the limit as x approaches 0 of sine x over x times 2x minus 1. Now you may recall that you can manipulate from the properties of limits. We could turn this into the limit as x approaches 0 and take sine x over x times the limit as x approaches 0 of 1 over 2x minus 1. Now this first limit is going to equal 1. That's coming from right up here. But the second limit is just going to be 1 over 2 times 0 minus 1, or negative 1. So now we can evaluate this limit as 1 times negative 1, or just negative 1. Alright, I lied. There's actually one more trick I want to show you which is getting a common denominator. Let's take a look at that and then we'll wrap up the video. Okay, I don't want to prolong the video, but take a look at this. If you plug in 0, you would get 1/2 minus 1/2 over 0, which would of course be 0 over 0, which tells us, hot dog, we might be able to solve this one. Okay, and the trick is to get a common denominator in the numerator. So let me, rather than walk you through it, let me just do the work and you'll see how the x's cancel out. Okay, might take a little bit of time to catch up with my work, but since I'm getting a common denominator and I'm getting the common denominator between 2 plus x and 2, I'm going to multiply the first fraction by 2 over 2 and the second fraction by 2 plus x over 2 plus x. Well, when I do that algebra, I have the numerator's numerator of 2 minus the quantity 2 plus x, and now I have my new denominator in the numerator of 2 times 2 plus x. I would urge you not to multiply things out. You'll find that the algebra is easier if you just keep it factored. So now let's simplify the upper numerator, and we'll get the limit as x approaches 0 of negative x over 2 times 2 plus x over x. Now these two x's cancel, and so I'm left with the limit as x approaches 0 of negative 1 over 2 times 2 plus x. Now let's try plugging in 0 again, and you'll see that I get negative 1/4 as my limit. Okay, so you've learned a lot of tricks here. One is to factor, one is to expand, one is to use sine x over x equals 1, and that's only as the limit as x approaches 0. And the last one is to get a common denominator. All kind of math tricks toward finding a limit. Okay, Ramblers, I know this was a long video. Thanks for watching. Hope it helped.